Thank you all for joining us today, both in person and on Zoom. This is our first in-person talk of the time. We have a couple more after this, so we look forward to welcoming you there too. And of course, yeah, thank you to everyone joining us across the world. We're happy to be able to have you join us as well. Today, our speaker is Chris Rackauckas, who is coming to us from MIT, where he is also the affiliated with the Julia Hub and Pumas AI. Chris will be talking to us today about scientific machine learning and how we can start integrating different data-driven methods into our existing engineering pipelines. And in particular, we'll be talking about how this will start evolving into the future. So with that, I think I'll go ahead and give it over to Chris.
Yeah, the scientific machine learning and agentic AI aspects. So because I added this extra little bit in there now, I won't probably have much to do with the whiteboard and such, but if anyone wants like the version that kind of goes into more detail and everything, I'm always happy to chat about all the detail, but I just felt like I needed to cut a little bit of detail in order to make sure I get through the whole story here. The story I wanted to give today was the bitter lesson for the bitter lesson. Where do humans go, human mathematicians and engineers in particular, go in the age of AI, right? The statement that where this kind of came from is this kind of discussion that everyone's having, which is, oh, do I even need to learn engineering anymore? Because, all these AI systems seem to be getting better. And I think that the answer is definitely yes, but I think that it's a yes and with an asterisk on there, right? So it's really kind of to go into what that asterisk is. So here's kind of like an explanatory diagram. I wouldn't put, don't put anything on the numbers. It's more for like the cartoon of the diagram. Like the idea behind it is the bitter lesson. Who here knows like the mythos of the bitter lesson? Yeah, so if you go to like Google or you go to like, Facebook's headquarters, they will all know the bitter lesson, right? It's kind of like the mythos of Silicon Valley right now, which is the idea of, it's this idea that kind of came from what happened with AlphaGo, right, and all these chess engines, where what they saw was that you can put human expertise into a system and be like, okay, if I see this part of the chessboard, then maybe I'll do this move, I'll do maybe this move or this move, and then sooner or later someone came along and just created a scalable method. It was a completely scalable, data-driven method based off a neural network, and it was bad. And then the data got bigger. It got okay. The data got bigger. It started winning. The data got bigger, and it became the best chess engine, right? The idea behind the bitter lesson is that, if you just work on methods that are scalable, right? Not try to make something that's efficient for one core, but just make something that's just a method that's able to scale to infinitely many cores in an embarrassingly parallel way, et cetera, and that can solve all possible problems, you'll sooner or later have enough compute and enough data that it'll be the best method, right? This is the mythos of Silicon Valley right now, where it really came across because of the incident that happened with the feed loop, where they found that, hey, look, this tree search-based algorithm, it only works based off of something that barely knows anything about chess. It's just completely a scalable algorithm. And a lot of the things that started happening with Silicon Valley today, they're all kind of proofs of the bitter lesson, or at least a lot of people think they are proofs of the bitter lesson, right? Large language models is an example of that, where it's using a technique that doesn't really know much about language itself, but if you pour the entirety of the internet into this process, if you pour all the data that we have, if you make your neural network large enough, then it becomes better than all of all the language translation tools that we had before, right? Because if you use the early internet, you probably use something like Google Translate early, but now all these large language model tools are able to not just get word translations, but they get things like slang correctly, they get words and phrases and all these extra details just because of the scaling, right? So the idea of the bitter lesson is don't work on anything that is specific, work on only things that are scaling, and as compute scales, as we build a new power plant specifically for these more AI machines, that will be the techniques that dominates, right? And so, the quote of the bitter lesson from Richard Sutton, right, is general methods that leverage computation are ultimately the most effective and by a large margin, right? This is a statement that I was trying to summarize in 2019, what had happened and try to set the view forward for how we should be thinking about everything we work on, right? But my statement here is that looking more closely at the AI successes might suggest that there is a bitter lesson that this bitter lesson needs to actually learn, right? And so, some really nice examples of this are, if you look at, for example, this case, so this is actually a case that's taken from a Tesla, right, where the Tesla actually stopped itself in the middle of the highway, and the reason was because the moon was very bright that day. And so it really took the moon from being basically a traffic signal, right? And so, this idea of, if we have enough data, we'll see absolutely everything. You can come up with a lot of these really interesting cases where you can say everything in data is, sampling from an infinite universe is pretty difficult to do to cover the entire space. Actually, one of my favorite examples of this is, you can see all these traffic signals hitting the car, right? And when it pans up, you'll see it's because it's driving behind a truck that has traffic signals inside of it, right? So this idea that, there's an infinite possibility of everything that it can do. And as long as you can sample an infinite data set in a dense way, you will then be able to learn everything, right? And your math brain should be thinking, there's no way to ever sample an infinite space densely, right? But the idea behind the scalable method is, don't worry, we never have to extrapolate. Everything is always interpolation if we get infinite amount of data and infinite amount of compute, right? But you can start to see that, there's always going to be some edge cases that are difficult to handle. And especially that's just within the data sense, right? Now, if you, I think that there's even something stronger to be said here, right? Which is that, let's say we have absolutely infinite data, right? So the case where people,
on Zoom, they're having trouble hearing you stand away from the podium. I guess it's trying to connect to that mic.
Oh, okay.
You don't mind standing close to that.
Okay. Sorry, I didn't know. I guess this must not be on. I just can stay here. Okay. Yeah. So what I was saying, right, is what I was saying is that people look at this idea that you can only you don't need to work on anything that's not scaling. And one of the reasons why you can start to pick at that is a very easy thing to pick at is everything that can go wrong with data, right? If you don't have the right data set for machine learning, then things can go wrong, right? And this is a very nice example of something that can be completely out of data, or out of your data set. But I think that the other thing that you can start to look at is, well, what if you give yourself infinite data, right? If you look at what happened earlier in the AI boom, it was put into the infinite data case automatically, right? So the reason why DeepMind and OpenAI and everything focused on game AIs very early on is because it's a very fixed scenario, right? Everything, your entire world is the video game. And so you can generate as much data as you want by running the video game effectively infinitely many times, right? And so all these game AIs to be able to play Mario, to play Go, and all these, is in this constrained environment, you could effectively generate any data set you want because you could keep playing the game. And in the context of this, it turned out, there was this thinking that was like, we proved that this bitter lesson does hold because in the end, things like AlphaGo, right? AlphaStar, all these things that were based on reinforcement learning were all of the things that won. But I think that if you actually go and look a little bit deeper into what happened in this space, you might want to put an asterisk on this win, right? Because, well, first of all, there's a lot of things that people found with reinforcement learning in this space where all sorts of difficulties in the learning processes were found. So, for example, I like to read the first one here. A coworker was teaching an agent to navigate a room. The episode terminates when an agent walks out of bounds. He didn't add any penalty if the episode terminates this way. And the final policy learned to be suicidal because a negative award was plentiful and a positive reward was hard to achieve. Right? What they're basically saying is, they're trying to train basically a robot to walk forward and be able to pick up a ball. But if it ever hit the wall, then it would, if it hit a wall, then it would stop the game. But the longer it took for it to get the ball, the lower its score was. So it learned it's actually very difficult to find the ball. So if I just go walk and hit the wall as quickly as possible, if the agent just runs in the simulation, it has a negative score, but it's at least better than the really low negatives that you get for finding the ball really late, right? And so, all these adverse things started coming into play with this reinforcement learning where you actually started to need to put in a lot of expert knowledge. And one of the things that we actually saw with all of this as well is that you started to see a lot of cost scaling, right? And just to throw a bunch of numbers out there, right? When people started doing AlphaGo, they started reporting some of these numbers saying like, oh, it's $35 million to be able to train AlphaGo to be able to be the best Go player, right? And for the first major runs, right? GPT-3 was a $10 million training run, right? And these are all numbers that were kind of posted online. And then you started to get to a point where you start getting some estimates instead, where you have external estimates and stuff, where Alpha Star, the StarCraft bot that was able to beat top players, which it kind of cheated by using Blink Stalker Micro, but that's a nice lunch topic. It actually took about $12 million for the final training, but about $1 billion in terms of the research tuning that was involved, right? You can start to see how the scaling looks, right? GPT-5 then was a $500 million training cost, but the total human cost put this as an estimated tens of billions, right? Which is why OpenAI right now is going for their next investment round where they say, oh, our next training is probably going to be on the order of $10 billion to be able to do the training, or $100 billion when you take into account all the human cost, right? Claude Opus is in the billions of dollar range, and so you could see that these are not increasing by two at a time, or it's not increasing linearly. These costs are increasing exponentially, right? Because what you're really seeing is that in order to have the next version of the model that is naturally able to be seen as better, you don't do so by making it linearly larger. You make it by getting another zero on the end, right? You go from having a model that has 3 billion parameters to 30 billion parameters to 300 billion parameters. And each time you have a very exponential growth in the cost when you're multiplying effectively each time. And so the cost of the AI training, right? Even for these things that we're saying, oh, AI is really good for large language models, right? Even in the spot places where we're saying we have all the data that we want and we can do the training, what we're seeing is that there's a few examples people know about, right? For example, there's the dormant 3 Mile Island, the nuclear power plant that's being spawned up just to be able to effectively feeding the next training runs, right? As I'm saying, these next training runs are going to be a cost that is about tens of billions of dollars to be able to do the training run itself. And that will require entirely new nuclear power plants to be spun up. We're going to have models that take, you have Sam Altman or Dario Amandi, the Anthropic CEO, was saying that they're in the $10 billion range for 2025. And then the next version, they're going to be in the $100 billion range, right? And what this is really showing you is that, yes, if you used ChatGPT v4 and then you went to ChatGPT v5, you're like, wow, that was a nice small improvement, right? What you're really looking at was a change of this was $1 billion to $10 billion. And then the next version that's going to be that next small improvement is $100 billion. The next small improvement is $1 trillion to trade. And if we really think that this is all going to just happen because we can only rely on scaling, we are actually hitting a point where that scaling cost is, we've let the exponential growth happen for a bit. And now we're really hitting the tail of an exponential. And in some sense, there are some that will make that will make the statement that the exponential growth is fine. We'll fund our way through this, and it'll solve all problems. Every LLM will get smart enough. But I think that if we look at this from another standpoint, it seems like if there's exponential cost growth, we should probably be reconsidering how much better these tools will be getting in the rate of improvement, right? The rate of improvement for these things came when the cost was a lot smaller, but now we are hitting a place where you can't just use more power from the power grid. The next improvement will require building more power plants than we've actually had in the United States. That's not going to be a quick improvement, right? And so if we're going to live in that statement, then I don't necessarily think we're going to see just the exponential increase that we've been seeing in the past, because we're starting to hit real resource constraints, right? And so then there's the question of if we're hitting these real resource constraints, but we know that these tools are getting better and they are improving, what should we be working on as people in this space who have expert knowledge or are not necessarily just working on, the scalability of the compute, right? I mean, there's a group that's always going to continue working on just making the compute more scalable and all these aspects. But if you're an engineer, if that's not your field, how should you be integrating with this world that is changing and improving, right? And basically, again, like this is like a, a pseudo graph, right? In a sense. So don't take the numbers 100% seriously here. But the idea here is that, there are some techniques like the purple line right here, which are using the things that are built off of these scalable techniques, but integrating our knowledge into them, right? And so instead of saying like, hey, look, we have certain types of techniques where we run, where I prove on the whiteboard the physics and I write something down and I write my own PDE simulator. This is one set of techniques. Then you have another set of techniques, which is these neural networks and data-driven techniques that live in a different world, right? Are there techniques where you can say everything that is gained from the world of more scalable techniques and these neural networks, can we build our expert knowledge on top of that so that we were kind of guaranteed to always be getting every improvement of the scalable techniques into our space? And this is what I kind of point to as scientific machine learning and the agentic AI for science as these two types of techniques, right? And there are two very different techniques. I'm going to show you exactly how they're coming into play and a lot of the current research that's ongoing with them. The scientific machine learning techniques are methods which use the machine learning as part of the physical modeling process, where the agentic AI are techniques that use the large language models and other related techniques as part of the process for developing the textual or code of the process itself. And I'm going to explain how both of those can be specialized towards scientific cases. So specifically, let me kind of go down this left branch here to start, just all about scientific machine learning. The idea behind scientific machine learning is there's a few different ways to describe it, but the way that I've been liking to describe it most recently is it's actually a problem of heterogeneous data, right? So if you think about what machine learning is actually working well on, it likes to work with homogeneous data, where you say, okay, I want text, right? I want text, and I just want more and more text. I want hundreds of billions and trillions of gigabytes of text. And you can train neural networks so that way they can take in a string of text and they spit out a string of text, and that's how you get large language models, right? And you'll go, okay, now I want to do machine learning on something like images of the stars. Okay, if I have a billion images of the stars, I can predict on the 1 billionth and plus 1th image exactly whether I have a black hole in that image or not, right? Turns out that not all scientific knowledge, though, comes in the form of homogeneous data, right? Like this data where you have the same number of rows and it fits nicely into feeding into your neural network. A nice case to describe this is, for example, general relativity, right? If I was to ask you okay, you probably believe that general relativity is true to some extent, right? But why do we know that general relativity is true, right? Is there any 1 billion row data set that you would use to train, a neural network, the entirety of general relativity? No, because there really isn't, that statement doesn't make sense because that's not why we know this physical law is true, right? How do we know that general relativity is true? Like one that everyone knows about is like, Thomas Eddington's, solar eclipse experiment, right? Where there was a solar eclipse that happened and you can see where the stars in the sky moved and that proved that gravitational lensing was the case, right? That was a data set that had 18 points where they looked at the movement of stars of 18 things, right? And that showed us that gravitational lensing was true, right? But then the other thing was, the perihelion of Mercury, right? If you look at the Mercury's around the sun, it does not go in a circle or an ellipse. It has a perihelion-like pattern, right? And that the explanation of the perihelion of Mercury and the way that it flowed around the sun. It was one of the ways that we actually proved general relativity, right? Another thing was gravitational lensing of galaxies, right? So there's all these little bits that we know in there, and we just say, okay, if all of these things are true, then this general scientific law must be holding, right? But if you're trying to feed that as a data set into a neural network, you can't be like, okay, I have images of all the same size and I can put this as my fixed length image into my neural network. Science doesn't work like that. We have heterogeneous data that we're trying to incorporate. But what we do is we find mathematical laws, these scientific equations that if you write down, if you write down the laws of general relativity, you can prove that you have, black holes. If you can prove that you have gravitational lensing, like all these different kind of features are kind of given from for these mathematical statements, right? So it's like an encoding of many different types of experiments and many different types of data into one representation. And so what we want to say is that, in some sense, these mathematical laws themselves are a source of data, right? We've used data to generate them. So they are our best encapsulation of a lot of information and data. Can we use them along with real data sources to be able to improve the way that we get good predictions, right? With the hypothesis being that, there's a fixed amount of data that you need to have in order to get a good prediction. But if I can get some of that data from the pseudo kind of scientific model, and then I get some of the data from the real world, I might need less data from the real world to be able to make the same good prediction, right? And then, so then the core point then from that is that if you can get more structure in coding your model, and that structure is scientifically verified or understood in some way, then maybe you can be able to get to more efficient learning. And one of the ways that we approach this then is what we call the universal differential equation. And the idea behind this is to use the universal approximator, right? Generally something like a neural network, though there are many other universal approximators that can work out depending on the circumstance. Things like Fourier series, things like Chebyshev series, and all these types of objects, right? Anything that is a universal approximator. The core thing that you want from machine learning is this idea that you can have an object that can represent all possible functions in a certain class of functions, right? And what we want to do is we want to be able to write down our physical models and say, hey, look, this is what I know, right? What I know is that if you leave bunnies in a room alone, then you'll get exponentially more bunnies over time. I know that there's an exponential here, and if I leave wolves in a room just with themselves, they all seem to starve to death. So if I get this exponential decay. But if I put rabbits and wolves in a room together, they tend to have an interaction, but my mother never ended up telling me what that interaction was, right? So there's some missing function to my model, right? So this gives you a way to be able to describe that, I know something about the physics. I know a lot about how the physics works, and I can write down a model, but there's something in my model that I don't know. But something in this missing function is required to be non-zero in order for me to be able to match the data and the phenomena that I see. What is the function that I'm missing from here? And what you can do with this is you can do things like, for example, train the neural network to be able to be a function approximator, right? It acts as the computational tool that spits out the right value for the missing part of the function. And then you can ask it for a representation, right? You can say, okay, well, once you have a tool that can spit out what this missing derivative is, you can always put new inputs in there, get new outputs, and it just always gives you something that's this correct derivative. You can start to ask questions like, okay, what is it sensitive to? What is this global sensitivity? What is this sparsity? Or what is this best polynomial representation of this missing function? And then you can have it spit out and effectively autocomplete the model where you say, I wrote down all the physics that I know, and then the machine learning has now helped me complete what the physics I didn't know was. And we can do this in example as a step-by-step process, right? The first thing that you can do is say, and so here's an example that's just using data from the first 21 days of, we train on the first 21 days of the COVID pandemic at the Wuhan region, and then we let it extrapolate forward. And what we do here is we just say, let's just do pure machine learning, right? So this is what you know as the neural ODE. It's U prime equals a neural network of U, right? And the statement here is that let this be a function that is described by any possible ordinary differential equation, and find a differential equation and let it extrapolate forward, right? Now, what a lot of people will say when they see this example is they'll say, oh, you train it on 0 to 21 days worth of data, so you train it here, and then you extrapolate. And the reason why this didn't work is because the neural network did not, because machine learning doesn't extrapolate well, right? And I think that is a terrible explanation. I mean, it's like this really easy thing to repeat. Machine learning doesn't extrapolate. But what really is going on here is under specification, right? What we're saying is that, let this system be defined by any possible ordinary differential equation, and we will train it on the data. So when you train on the data, you're basically just putting a constraint on that statement, right? So it's now, let the system be defined by any possible ordinary differential equation that goes through this data. Pick one of them at random, and now see what happens when you extrapolate it. And oh no, it found a linear equation, something that's kind of linear instead of kind of exponential, right? And the reason that what's gone wrong here is we set any possible differential equation that fits the data that is way too big of a universe of all possible functions, right? So the real thing with scientific machine learning here is to ask the question of, can we constrain the set of possible functions that machine learning is allowed to learn to be a set that is more likely to be true given other things that we know about the system, right? And it turns out that we do have a technique that for constraining function spaces, and that is actually mathematical modeling, right? We normally don't describe it like that, but we normally describe it in the other approach, right? Where if you write down a mathematical model, you start to teach your students like, oh, if I have these relations here, then I have a conservation law. Or if I have these relations here, then the solution is always positive, right? But it turns out that if we want to do function learning, that's exactly the kind of things we want, right? We want to be able to say, hey, the solution of any model should have that the number of people exposed to the disease is always a positive number. You can't have negative people exposed to the disease. And so if we want to be able to then express, this learning problem in a space where all of our scientific ideas are encapsulated, what we can do is we can effectively do the inverse of why we do ODE modeling, right? Because when we do ODE modeling, we write down the ODE model and then we say, oh, from this model, I can show you that, there is a maximum to the population. I can show you that there's a conservation law. But if we want to do machine learning with conservation laws, we can use exactly that same structure, right? And so this gets us to this universal ODE form, which, again, that's a very different explanation that you might hear in many contexts, right? And so one way to look at this is to say, hey, look, this is based off of an SIRD model, right? So susceptible individuals become exposed, exposed individuals become infected individuals either recover from the disease or they die, right? And so if you're awake during the pandemic, you probably heard a million people tell you about SIR type models, right? And so this is just one of them. It has a little bit more structure to it than just the pure SIR. And so you might want to say, hey, look, the neural ODE did not do well on this problem because it didn't have any scientific knowledge. And now I did a training problem where what I did is I wrote down an SIRD model. But what I didn't know was I didn't know the exposure term, because the way that people got exposed to the disease was very different in Kansas than it was in Boston, than it was in Sweden, where there was no lockdown, right? And so if I don't know how to write down the algebraic term for exposure, I can put my neural network right here, and then I can just learn this little bit. And now I've done machine learning I know some epidemics, and I did some machine learning with it, and look how much better it did, right? And this tends to be a lot of the explanation that you get in some of the scientific machine learning literature. I infused my scientific knowledge with the machine learning, and it did better, right? I find that that's a very hand-wavy explanation for why this ends up working. And there's a much better explanation that can be found here, right? So if this unknown portion is supposed to be the exposure term to the equation, let's assume that we take the absolute value of what comes out of the neural network. So it's always a positive function. It's always a positive value. So our neural network is effectively a universal approximator over the positive space. And we put the same neural network here as we do down here, right? So the same term, you just put the same number there and there, right? If you do that, it turns out that there's a lot of nice things that this representation has. First of all, you see that there's a minus term for every positive term, minus term for every positive term, minus plus, minus plus, minus plus. And what this means is that S plus E plus I plus R plus D is always equal to a constant, right? You know this from ordinary differential equations. This is a thing that people would prove. Normally you'd write down your model and then you say, oh, now I proved I have a conservation law. But now what we're basically saying is this is a formulation for me to learn the time series on the right here that enforces that this conservation law, that everybody needs to be captured in one of these buckets, and that must always be true going forward. But not only that, if you also have minus here, minus here, minus here, and all these are positive values, then S prime is monotonically decreasing. Basically, this is encoding the assumption that at the beginning of a pandemic, people are susceptible. People are no longer susceptible to disease because you have more and more people getting this disease, and no one has been able to recover to be able to get back to the state yet. So we've encoded an assumption in here, kind of by using an epidemic formulation, right? Another thing that happens then is that if S prime is always decreasing, you can actually prove that there is a critical point for E and there's a critical point for I, which means that there's exactly one maxima for the number of people are exposed and one number of people who are infected. And so you can call that that is the peak, right? Normally at the beginning of any pandemic, you always have a peak. And so what this is really encoding is that, hey, look, the conservation laws that you expect to be true are all there. S, E, I, R, and D, all of your values that you know are supposed to be positive, they are enforced to be positive because of this ordinary differential equation form. S prime is monotonically decreasing, which you expect to happen at the beginning of a pandemic. And I has a peak, right? There's going to be a peak number of infections. Given that all of these things are true for the function that I'm learning, now fit the time series. right? So you can think about this instead as a problem of I've decreased the function space that I'm allowed to sample from. It's still going to take a random sample of a function, right? It'll learn this random sample of a function, but the function that it is allowed to be, the function predictor that it's allowed to be is something that must have the conservation laws correct, must have S prime monotonically decreasing at the beginning, and must have some peak in I sooner or later, right? And you can see that from that same time series, it fits, and it gets a much better prediction than the neural ODE one. But the more interesting thing to kind of almost see here is that if you let this extrapolate out, you'll actually see, hey, look, this is actually kind of shallowing out. It's decreasing because by definition, it is impossible for this training process to not have a peak, right? Again, I did the verbal proof of why it is. So I think that while there's kind of this hand wavy explanation for why these kind of scientific machine learning techniques work, and it's now kind of gotten a lot of usage outside of us, I encourage people to kind of look at what's going on here from more of a lens of enforcing properties on the functions that you're learning, and then forcing that you pull from that set of functions that enforces the property, right? And then next nice thing that happens when you do this as well is you can then start to interpret it, right? So once we train the neural network, we can do things like run symbolic regression on it. So, I know that everyone here would know things like the STLSQ type of symbolic regression method, right? That's the Stephen Brunton's symbolic regression method. That's half of the Cindy algorithm, right? So if you generate a data set from your neural network and then you just run STLSQ on it, right? You'll get a set of polynomials or linear combinations of terms from your library, right? And then from that you can start to say, okay, this is the best representation of the term that I had in the neural network here, right? Now, we see two things when we mix sparse regression into this learning process. One of the things that you see is that it generally improves the generalizability. This is a very difficult property to prove in general, but we do see that this kind of works for similar reasons that low order polynomials seem to get better extrapolation than higher order polynomials. There's some ancient proofs in the numerical analysis literature as to why that's the case. It seems like there's a similar kind of tail property. We're having difficulty finishing up that work, but there's some justification as to why we empirically see this property. But the other thing that happens is this interpretability. So in this process, we allowed the term for exposure to be a function of the number of people who are susceptible to the disease, number of people infected, and the number of people who have died. If you look at what we get from the sparse regression term here, you see that D does not show up in this equation at all, which is effectively a hypothesis that exposure to the disease is not caused by people who are already dead, which should be true for COVID-19, right? But you can see that if you have enough model structure around it, the terms in your models actually have some meaning. And when you start to do this identification process and you start to do this sparse regression process, you can start to mix back in some idea of getting this meaning out through some of these techniques, right? Now, of course, in this technique, when we start putting these out, I think the best use cases are all started coming from real scientists who started using this in their domains. So here's, and so we started, if you want to see how to use all this stuff yourself, what you can do is you go to docs.sciml.ai. You can go down here to, for example, automated model discovery. And here's one example that came from that published paper, which is effectively doing what this process of saying, okay, we have two black holes that are we have two black holes that are in a binary system, but black holes have sufficiently large mass that Newtonian dynamics does not work out well, and so you need to have general relativity corrections. So let's write down the system assuming only Newtonian physics, but learn what the general relativity corrections are. And this tutorial then shows you how to do all the steps of this problem, where you first it gets the data set, and then it writes down the version of the model. It writes down the version of the model that has the Newtonian physics written down, plus a neural network to capture what we don't know about the physics. And then it trains the neural network with respect to the missing parts of the model. And then you actually see that what comes out here is actually, again, I mentioned the perihedron of Mercury, right? Newtonian mechanics, so the starting point, Newtonian physics gives you that if you have a two-body system, you have an ellipse as your analytical solution, right? But if you then do this with the relativistic correction, corrections, you have a minor correction that ends up kind of causing a drift over time, and this causes the Lissajy pattern that you see here. And that's exactly what we know from the two-body problem solution to these larger, having at least one large body, right? That's the general relativity solution. That is the perihedron of Mercury, right? And see this naturally evolved just out of, this saying, okay, if I cannot fit the data if I only allow myself to have pure Newtonian physics, so please give me a correction to this term, and that correction of the term ends up giving you this longer term pattern. Yeah, so even with a small amount of data here, right? So it only trains on the very, very, very tiny bit of the time series at the beginning. That gives you enough to learn the difference between what is Newtonian physics and what must be happening in black hole dynamics, such that when you extrapolate that into the future, it's able to be it's able to give you a fairly good prediction, right? And so again, if you want to kind of work with these techniques, see these techniques in person, I highly recommend you go to the tutorial, start to run them, and then you'll start to all these questions that you might have about, okay, what size neural networks do you need to have? How much data you need to have? A lot of it comes from understanding the usage and seeing this. But one of the things that you'll see with this kind of method is that when all of these examples are very, very extremely living in this data poor regime, right? Again, we're saying 21 data points here. We're saying, I think, like less than 100 data points for this one, right? We're really saying, can we do machine learning with 100 data points or less? Because, getting our next data point might be another $1 billion experiment. So can we use these techniques in a way that scales? And then this answer is to say yes and, right? Yes. What we could do is we can use all of our physical knowledge and we can try to make the machine learning is still there, right? It's just we try to make as small of a machine learning as possible in order to make it scale better. And you can see that inside of the code here, right? If you look at the neural networks here, this will probably be the most itty-bitty neural network you've seen. It just has 2 hidden layers, and the layer size is size 32, right? We're talking tiny neural networks that can represent, very simple functions that we're then incorporating with a lot of behavior, right? It's this approach of a lot of behavior with small neural networks, and we're using what we know from what we're getting from machine learning as selectively as possible. Almost like an approach of being a skeptic of machine learning, but incorporating it into what your work is. One of the ways that we've actually started to use this in practice, so this is actually with the Williams Formula One team. What happened here was so when they do the races, they have these speed over ground sensors, and they have to be really cheap and sensors because the aerodynamics team does not allow their sensors to affect their car design at all, right? So the sensor team has to basically hide them in there in the worst spots, and so you have to make do with whatever sensors you can. But what these sensors are used for is they used to be able to find out what the angle of approach is as they go along the track, right? So the reason why this is done is because before a race, before a race, you have all these mathematicians and engineers design what the best way to drive through a given track is, right? They'll go through this track and they'll be like, okay, you want to take this approach like really close to the edge, and you want to go further out on this one, and if you do that, you'll be able to keep the most speed, right? So you have entire crews that are just designed to find out what is the optimal way to drive the laps, right? But then when you put the driver on the racetrack, you want to ask the question, are they actually driving like the optimal approach says it would be? And in order to do that live, what you want to do is you want to get sensor data back, which is just a speed over ground sensor. But again, that speed over ground sensor it has to be a small little instrument because it can't affect the aerodynamics. And so it's a really poor sensor in a sense. And what you need to do is you need to be able to back out, how do I get good enough information about angle of approach so that way I can live if you ever watch the races, you'll see that they're live calling into the driver saying, hey, you keep on taking this turn too close to the angle. You need to angle this one out. You take it at 40 degrees, take it at 45. Right. And the way that they're getting this information is they're taking the information from the sensor and then they were running it through a Gaussian process. So it's just a pure machine learning approach. But what we did was we built out a vehicle dynamics model of the car, and we said our vehicle dynamics model of the car is still missing some major factors, such as, for example, if you turn your wheel's not going to, you're not going to actually capture all of the angular momentum because you're going to have slippage of the wheel because, your tires are sliding at the speed at which the Formula cars are driving. But we'll write down a vehicle dynamics model, and we'll allow ourselves to be, have incorrectness here, here, and here due to friction, due to, wheel slippage and such. But we should be able to be in the right path. And what we saw between these two approaches was, so this Python one here is, what you'll see as the car is the prediction of what the angle of the car is at the given time versus the true angle of the car as a color underneath. You'll see that the approach that is using the scientific machine learning on top of it gives you a much better, smoother prediction. One of the reasons why it's smoother is actually because we're predicting on the second derivative, right? We're predicting on the angles, and then we're taking the integrals, and so you naturally get a smooth prediction. But then you also just get a solution that is much more accurate in general. And so this was something that, while the first one meant that they weren't really able to call into the driver and give pretty much any information, because when you take that along a current, they go, you were somewhere between 30 degrees and 45 degrees, and the optimal is 37. Our error bars are too large to basically give you something back here. Now is able to be something where they can get live information back to the driver to say, hey, look, now you can use this to improve the angle of attack. And then I like to show that, if people don't think that scientific machine learning is, hold on. People don't think that scientific machine learning is cool or going to industries is cool. Well, I'll tell you that we actually got to do this with the driver. So that is the, George Russell, the driver, now he's on Mercedes or whatnot, right? And so we actually got to go on the car, got to meet everyone from the team. And so, the result is math is cool. And if you wanted to go do cool things, a lot of people, scientific machine learning is going everywhere. And so there's a lot of cool stuff that's going on in industry as well. That's my, stay in school kids, kind of a part of the talk. Now, there's a lot more examples I could talk about with scientific machine learning. I'll cut that version of the talk there to say there's a version of the talk on YouTube, this accurate and efficient physics-informed learning through differentiable simulation. This talk goes through all sorts of different examples, like, more race cars, more, airplanes, automobiles, et cetera, showing that this idea of, you write down all the physics and you improve it with the neural networks, works in a lot of different cases. So a lot of chemical cases, biological cases. I want to get onto a different topic, but if you want to see more proofs of that, that's a talk that will go into that. I will say that there's one thing that really kind of came into play to kind of show that this was an interesting case, right? It was brought up that I have a pharmacometrics background, and one of the things that we did early on with this was we were actually working on these models of mRNA vaccines to be able to find out, like, what is the optimal way to be able to take an mRNA vaccine that is used on data for adults and be able to turn that into something that you can prove is going to be safe for a child, right? And the most difficult thing about building about this process, right? A lot of people think, I learned all this stuff about ordinary differential equations and I'm a mathematician, so what I'm going to do is I'm going to make the ODE solvers faster. I'm going to make them more accurate. I'm going to work on higher order solvers, right? But in the real world, what we saw the actual problem was how do you actually figure out what equations to write down right here? So what we did was we started working with Moderna. So the software that we worked with and some of our scientific machine learning techniques and the auto differentiation was actually behind a lot of the stuff that went on for the Moderna mRNA vaccines for COVID, where what it was really used for was helping this process of finding out which factors should you actually be taking into account in the equations. And if you see all the stuff that we did before, right, how do you solve this problem of which genetic factors do I put in my equations, which other blood factors and such do I put in my covariate equations to be able to predict whether someone will respond to a drug or not? It became this problem of can you train a neural network and can you do the sparsification, right? Because as I mentioned just a few slides back, right, I mentioned, here's a case where we let the neural network be a function of S, I, and D, and it became only a function of S and I. You can see how if you just say, okay, now let my vaccine be something that is a function, my vaccine efficacy be a function of all sorts of different things, every single genetic factor you can think of, everything in a blood screening panel, etc. Now give me the ODE that describes the dynamics for how the PK, so the amount of the drug inside your body, but also the PD, the effect that this has on you for whether you show flu symptoms and things like that, right? What we're able to show is that you can use the same approach where you say, I can put a neural network in here that is a function of all these different variables. I train it, so now I give you now I have a really good prediction of the PK/PD profile of every individual. But when I run the sparsification, it starts to tell me, these are the factors that actually matter. These are the factors that don't matter. And so it becomes much easier to then build your model because the process of a building model then becomes a multiple choice problem, right? You go from what in the world what in the world is mRNA vaccines? What are they supposed to care about? Do they care about, your blood pressure or, and this becomes a thing of, the machine learning said that there are these 10 factors that you should look at. Maybe the model doesn't need all 10, but we've identified that, at least with these 10, you can explain all of your data, right? And so then the true modeler can go back and start to write down those equations. Is that a completely automated approach that will do machine learning for you, everything for you? No. Is that something that you can write down a factor to say, hey, look, my loss function was 0.5 and now it's 0.4 and you can get a NeurIPS paper? No, but that's how you would actually use it in practice, right? It's this process of making it more easy for you to come up with the right equations. And then that's actually what made, that makes, the fastest vaccine trials ever, right? So I think that's a way to be thinking about how, these techniques are incorporating machine learning into the workflows of what we're doing as scientists, not necessarily replacing them on all aspects. Now, the other branch here is a branch on agentic AI. How many people are actually using agentic AI tools for coding? Okay. All the students don't have their hand up. I know that you're cheating on your quizzes. So we've been developing something that is a tool for agentic AI in modeling and simulation. Just kind of show you what this tool looks like with the non-AI part, right? It's a system for doing drag and drop components where you put together these components and you generate models using these. So how many people here know things like Simulink? Yeah, and how many people know Modelica? Okay, yeah, almost nobody in the United States knows Modelica for some reason. So this tool is based off of a differential algebraic equation formulation, which is similar to tools like Modelica or GPROMs if you come from the chemical process engineering field. And we could go into all the details of DAEs and why that's the case. But basically, the idea behind it is it's a system for which you can have pre-built models. So you can have a model of a car, you can have a model of a battery. These can be entire partial differential equations, but when you stitch them together, it has a schema for how it knows how to create the composed simulation. So that way people can work in isolation and build out complete scientific models. But if you want to compose all these models together, it will, you just push buttons and for how they compose together. And the generated model from that it will automatically do things like conserve energy, conserve mass, conserve conservation of momentum. And exactly how it finds all those conservation laws is a separate topic, but we could go into that in detail in another time. But yeah, so what I wanted to get to, so that's why I had that issue. A lot of people know that a lot of these tools that are already starting to be used for coding, right? These LLM tools for coding include things like Gemini 3, Sonnet 4.5, right? This actually took the screenshot before Opus 4.5, and now there's Opus 4.8 or 4.6, right? But there's a lot of these general purpose tools that they're designed for, if you take in just some code, or if you ask it some prompt, it can generate some code, right? And the way that these systems actually work, though, is that they have this write, execute, fix, or read, fix loop, right? So, you might think like, okay, I've used ChatGPT before, but it didn't seem to be that accurate at, it couldn't even figure out, my mother's name or something, right? But the way that these tools are actually able to give you accurate code is less based off of the accuracy of the large language model themselves and more about the agentic loop around it. Because what they do is they'll write code where the writing of the code, it comes from this large language model, but then it gives it, and when you call it agentic, what it means is it has the ability to be able to actually execute that code, read the error messages that come out of it, and then try to fix the code and then write new code, right? And so it has this loop that it goes around where it doesn't just try to do something once, it tries to write code, but then it tries to find out if that code is correct by attempting to execute it, right? And so there's a bunch of these different tools, and I give different workshops on using these tools and such. The main one tends to be Claude Codes these days, but Codex, But the key thing that you might want to ask is, if these tools exist, right, and a lot of people are starting to adopt them for generating code, is there anything that can be done beyond what they have for improving specifically what happens when you say want to build differential equations or build physical models, right? So Okay, so then and so that connects into the earlier part of the talk, which is this question of, well, I just told you that, it's going to take, it's already $10 billion dollars for this training. And so the next version of, the next version of ChatGPT is $100 billion dollars if those power plants actually get built. I think that is a great lunch topic to ask if, the $500 billion dollars Stargate project is actually going to happen. But if those actually get built, they, still be a small increase. And then you need to have the 5 trillion version before you get the second increase, right? Given that these things seem to have a fundamental accuracy limit and they're kind of leveling off in their improvement, is there anything that we can do so that way the AIs that exist for today are actually better for generating code for engineering, right? And I think that you can really start to see this because, the LLMs themselves, like this $100 billion problem is just this right part of the system, right? It's just writing code. So we can say that, yes, if the first code that is written down by the LLMs is improved, that will make these tools better, guaranteed. But are there other ways by which this process can improve, right? There's some research that came out of NVIDIA that I think really started to point in this direction, where they showed, they asked this question of, are small language models actually sufficient, right? If we actually have an inaccurate thing for writing code, but you give it this read write eval loop, and you give it a decent enough compiler, is it able to fix itself? And what they were able to show in many different ways was that small language models with the right feedback we're able to almost match the accuracy of large language models. And so that should kind of start to be like, like if that's the case, then it seems like the accuracy of our ability to generate code could actually be really highly impacted, not just on the LLM, but all these other aspects around it, right? And so the question is, well, can we take that idea and what would it mean to make this be better? Like what would it mean to make a language that is more efficient for large language models to be able to get accurate code, right? And we came up with a hypothesis here, which is that, the key thing that we see happening in this read write this loop here is that it really the earlier that it can get errors about when I got something wrong, and the more clear that all these errors are, the quicker it's able to then start to iterate and be able to fix itself. So if we can design a language for writing down our differential equations that enforces more things to be correct early on, then we can improve the agentic accuracy, right? This gave us the idea behind the piece of dyad, right? So this is what the dyad language then looks like. It's a language that is kind of a derivative of Modelica with some changes, where there are a few things here to kind of point to, right? One is that it's a unit-based language. So if you write down any equation that has units, it also has a static analysis check that can actually find and say, this equation is correct, this equation is incorrect. And it won't compile if you have equations that aren't unit correct. And we'll actually see later in a demonstration here that the agent's able to use that and basically say, oh, equation 3 is not unit correct. And so therefore I was missing the parameter for the specific heat of water inside of this equation, right? It's able to find out these factors because it's getting feedback from the compiler about the non-physical accuracy of equations. Another thing here is that it's a symbolic language, symbolic declarative language, where any relationship between derivatives and variables can be written down. It naturally generates differential algebraic equations. Now, a lot of differential algebraic equations are not necessarily solvable by numerical techniques, but then there's a symbolic process that transforms them into something that is numerically stable, right? So we separate them with the approach of, the user here does not actually have to write something that is a formulation that is good to solve with. They just have to write down equations that are physically accurate. And then we have a process that will turn that into numerically stable equations to actually then run the solver on. So it's a language that is by design separating the implementation of the solver from the representation of the physics. And the last thing is that it supports composition of models, right? So if you have a pre-built model for a car battery, a pre-built model for a drive shaft, you can connect those two things together and it'll fully reuse that pre-built model. And the reason for that is because if the LLM is making less guesses about the code, then it's more likely to be correct, right? Effectively, if someone took the time to write down a whole battery model and they spent the 5 years of their PhD coming up with all these images and being like, I know when my battery model is correct, the LLM should just say, battery goes here and reuse exactly all those equations rather than trying to create a new one from scratch, right? So we started with this hypothesis that said a language that has these features should be something for which you have much more accuracy from LLMs to be able to generate accurate differential equations and thus accurate models. And this actually has been what we've been evolving into this dyad system. And this is what we're now using throughout industry and How much time do I have left?
It'd be good to wrap up soon.
Yeah, so I'll get to the last part here, but basically, if you're interested in these kinds of tools where you build models and such, it has both a coding interface and it has a graphical interface. So we're using it throughout different industry cases. But the reason why I bring all this up is because of the agentic aspect. So I'm going to jump way to the end here, though. If anyone wants to talk about all the control stuff, I'm happy to go into details. The reason why I bring all this up here, though, is to show you this demonstration of what it looks like to actually use the agentic AI coding to be able to see what happens with the accuracy of this system. We have papers that have just gone online that are showcasing how it's improved accuracy over things like just using a standard LLM and such. But I think it's more informative to kind of see it with your own eyes. So. Hold on. I think this is not doing the audio.
And bring the vehicle to a stop.
Can the people online hear the audio with that? This is the SciML version of the. All right. Oops.
In this video, we will build a friction brake system model using an agentic workflow with dyad. When the driver presses the brake pedal, the braking system applies a force, causing the brake pads to clamp onto a spinning disc or drum, thus creating friction that resists the wheel's rotation and can bring the vehicle to a stop. This friction creates heat that causes the brake pads and disc to warm up. Engineering a brake system requires meeting both mechanical and thermal requirements for safe vehicle operation. Utilizing a modern workflow to engineer this system requires physical models of the friction brake in the vehicle. Here we will develop system models that are typical of the ones required for model-based systems engineering. But we will do so using an AI agent, basically by posing the problem that we want to solve, and ultimately ending up with models that execute and predict the mechanical and thermal dynamics of the system. Agentic workflows are fundamentally altering the way that the human and computer interface works, leading to the potential for massive gains in engineering productivity and efficiency. These agentic workflows are a core part of our dyad product and will be demonstrated in this short video.
Yeah, so what's saying is that the model is completely generated through just prompting
We start by asking the agent to help us create a model for the friction brake that can capture the relevant physical interactions. The agent then does research and provides a mathematical formulation that meets our specification. This step alone is massively helpful. With just one simple query, you potentially have a model that can be implemented immediately, along with reasonable parameter values that are representative of our application. We can even easily iterate on the model by asking the agent to refine the formulation. As you can see from the responses, the agent plans and then returns with a new formulation, including nicely summarizing the changes requested. These changes can be as complex as asking for different mathematical formulations for the physics, or as simple as changing the interface for the model. Once we are happy with the formulation, we ask the agent to implement the model for us in dyad. The agent knows which component primitives are available and utilizes them to implement the model. Now we have executable, fully parameterized code that represents the physics. Note that the code is well documented and very nicely formatted. We also ask the agent to create a unit test that exercises the model under specified boundary conditions. We can test that the component is behaving correctly and also subsequently use these tests to help refine the formulation and model parameterization. This agent is not just capable of generating the model code, but is also contextually aware of the models we are creating, the relevant physics and expected responses, and also key numerical considerations. We now have one part of the model that takes a brake command and generates the resulting friction torque and heat based on the vehicle boundary conditions. Because we are also planning to work with the model moving forward in a graphical interface, we can add an icon to the model. This icon will also appear later in the video when we use this brake component in the full system model. We can go through the exact same process to develop the thermal model for the brake. This part of the model will provide the thermal dynamics of the brake system. We start by asking the agent to help us create a thermal model for the brake system that captures the relevant thermal interactions. Again, we go through several iterations on the model formulation, model interface, and model parameterization. Note that the agent is also reasoning regarding our proposed formulation changes. It even provides us information back regarding how these changes will impact the thermodynamics in different temperature regimes, so that we can evaluate whether these changes are appropriate for our modeling needs. After we ask the agent to implement the final model formulation, we again ask for a test case to help validate the model. Note the really interesting interaction with the agent. The agent knows how much heat is put into the system in the test, and notes that the heat in the model does not balance, a sign that there is potentially an issue with the energy balance in the model. The agent then performs an energy analysis by looking at the individual terms in the equations. The agent rightly concludes that the system has not run to steady state, and thus should be run longer, and proceeds to do so. This is completely unprompted, high-level thinking by the agent, providing insights that can help even experienced engineers rapidly develop and validate models.
Yeah, so this goes a bit more, and we built out a whole vehicle dynamics model as part of the video. If anyone's curious, all these videos are online. We have a few videos like this as well. In fact, what we started to do, we got enough confidence in the system that we actually run a live show on Fridays now on Twitch and YouTube, just showing people, because this looks like a canned video, and a lot of people started telling us like, oh, did you make sure that this worked beforehand, right? And so what we started doing was just said, okay, the only way we can convince people that this works is we'll run a live show where we'll take your things from Twitch and we'll implement it live. What we last did was we built out a whole model of a quadrotor, and so we built out a model of a quadrotor, and then we built a game where we can actually move the set point that is supposed to fly to, and the whole control system was generated for it and everything as well, and it used the libraries to generate that. And so actually tomorrow then we'll run a next version of that where Ben Chung, who's actually was a postdoc here, and he was in the aero department. He'll hook up a PlayStation controller, and will generate all the drivers to be able to do this based off of all agentically, and then also generate the C code that will then actually make this run on a device. So yeah, it'll be a fun kind of thing. But what I'm basically showing here though is like the way that this agentic system works is not necessarily based off the accuracy of the LLM. Right? What John described here was that it had the ability to be able to, again, check all the units of the equations. And so you'll see that as it's going through this process, it finds like, oh, I have a unit inaccuracy in this equation, so therefore I'm missing the specific heat of water in this term, right? And that's like, so it finds missing parameter terms because of unit analysis. But then it also does things like it runs the model, finds that it's not reaching balance, so therefore it's not at steady state, and it has to then reason about what goes from the solution, right? It's that connection of the LLM to the process to be able to run models and run analyses, and then that when you start to force them to say, all of everything that you know about the system must be true, make sure everything together is true, and you have the access to be able to run it, keep on running the code. That loop then makes it so that way you can generate more things more accurately. So yeah, we have a lot of examples of that going through, and we'd be happy to see anyone if you're curious about how all this works. We could get this up and running. If you want to just slap in like, oh, generate for me a discretization in Navier-Stokes or something, and see how well it's able to do your favorite problem. So thank you.
Thank you so much for that talk. So there's so much cool stuff to follow up on here. But first, we'll take any questions here in the audience, and then we'll open up to questions there on Zoom. I've seen that. So anyone here have a question?
Yeah, I had a question about like a lot of people here work on Cindy, and you talked about it a little bit as well. Can you say a little more about like how you see this like sparse recovery and the UDEs working together? Are they complementary, or?
Yeah, I think they're quite complementary, right? And I think. Yeah, so the question from the Zoom was that, a lot of people here work on the sparse regression techniques, and, we do some of the techniques with the UDEs, and are they complementary or not? And I think that I think that this example is not as easy to show that it's complementariness, because even though this is a really nice illustrative example, you could look at this and go, well, how does Cindy work, right? The first thing that you do is you put a line through your data points, you get the derivative estimates, and then you perform a sparse regression, right? What you could do in this case is you can take all your data points and you can say, well, I can define all these functions, I can build them, I can subtract them out, and I can do sparse regression directly on this, right? So in this specific case, you could come up with a modification of Cindy, so that way, you could do the sparse regression isolation, right? But then as you start to get to more and more difficult cases, it becomes difficult to figure out how to incorporate all your prior knowledge into this Cindy process, right? So for example, if you had a differential algebraic equation here, right? So you have an equation that has like, two derivative equations and then one conservation law, or if you have, for example, equations that have constraint equations, so you have inequalities are also included in the system, right? It's not necessarily clear how to be able to create a version of Cindy that does all these, right? But if you have a differentiable simulation process that's able to solve those types of equations, right, then you can train the neural network in this context. And that neural network is a representation of the function that goes there. And then you just apply symbolic regression on that function, right? And that's actually one of the things that bailed us out in the context of this learning problem for the pharmacometrics models. I'm not going to give a full description of how nonlinear mixed effects works, but nonlinear mixed effects is something where you aren't actually just doing the fitting of the dynamical system, but you have a population model on top of the dynamical system where you have to enforce that a population of eta parameters ends up having an expected value of 0, and there's so it becomes this whole. There's a way to write it all down as a maximum likelihood estimation problem and create an optimization scheme to get all these different parameters. But then at the end of the day, it can be very difficult to understand, how would you do that in isolation? So what we could do, though, is we could say, hey, look, the theta parameters don't have extra constraints like the etas. So what we'll do is we'll do the same exact maximum likelihood procedure, but now we'll make a neural network that is a function of the thetas, and we'll stick it right here. And then, we're able to train that neural network to be this missing function. And so that way, the same maximum likelihood estimation, the same statistical estimation and uncertainty quantification is all done, just like it was a normal pharmacometrics model, but we now have a missing function, and now I can just pull that out in isolation and perform sparse regression on that, right? So I think, that's why I kind of think that they kind of work together in tandem, because if you ever have any, basically any kind of prior knowledge about how a system works, you can usually write down a simulation, right? And what you could do with this technique is you can say, write down the simulation and put a neural network for the thing that you don't know how to do. Once you train that neural network, you can pull it out of your simulation and just start to ask the question, what did I learn, right? And what did I learn is exactly what all these symbolic regression techniques are able to very nicely solve. So I put the two together. I mean, again, in very specific contexts, you can probably prove there's a way to do Cindy that takes in this case. There's probably a way to do Cindy if you have multiple multiplicative neural networks as well. But every modification to your prior knowledge would be a new, paper, which is good for getting academic papers. But if you want to just be okay, I want a solution in a month, right? Well, you could just slap a neural network in there and just perform your same old Cindy, and you're good.
Take questions on really quickly. So there were a couple of the comments here.
Yep.
Just a logistical one. Will you be able to provide the slide deck that you have?
Oh yeah, I can put these slides up. Yeah, for sure.
Then just talk about the YouTube Twitch channel, and when someone responded, that was YouTube at Julia Hub.
Yeah, the Julia Hub channel does it, and I think it will have right now that there's a live video going tomorrow or something, right? So there's a link. I think on the West Coast it's going to be 7 a.m. Because we also do this in Europe time, so we'll have to probably find a later time. But if you guys want to wake up early, while you're brushing your teeth, you can do some agentic engineering. So.
Someone asks, what's the difference between dyad build PKD models in dyad?
Dyad is completely not about PKPD models at all. So dyad is about, you can build a dynamical system for these, right? You can build any kind of differential equation into dyad, but the PKPD models are generally mixed with this nonlinear mixed effects model, which is a population model. Then this population model is basically trying to what the population model, what these things are trying to solve is effectively the problem of if you have a different weight or if you have a different sex or other very easily predictable factor or easily measurable factors, how does that affect your dynamical system on average, right? So everybody's a little bit different, but on average, how much does being a man versus a woman mean for your drug metabolism for a given drug, right? Because that might mean that, for given that factor, you might need to give some part of the population a different dose than another population, right? And so the PUMAS is all about solving this nonlinear mixed effects problem, which is the statistical model on top of the dynamical system and being able to learn these statistical factors, right? Dyad does not have the statistical modeling at all, but it has a lot of pre-built models specifically in other domains, such as, electrical, rotational, so hydraulics, batteries, multi-body systems, so like robotics and HVAC systems, and it has the ability to be able to compose models automatically using a differential algebraic equation structure. So one of them is really focused on like aerospace, automotive, industrial HVAC systems. The other is really focused on the kinds of analyses that you have to do in clinical trials. If you're interested in kind of learning a bit more about what the composability aspects are, if you haven't seen this before, because it seems like I got some like nobody here is really a Mandelica person, but it seems that's mostly only Sweden anyway, so I kind of expect that. I recommend you check out the open source piece, which is a compiler. It's modelingtoolkit.jl, which goes into how acausal modeling works and why we do everything with differential algebraic equations. It gives an explanation of a lot of the details about how this connection process automatically gives you conservation laws, Kirchhoff's laws, and all that. And once you see that, you can kind of start to see why this is an approach for automatically generating the composed model system. And if you're curious about the math, just as a thing, you can go to Modeling Toolkit course, and we ran a course, a special course that then goes into the math of the differential algebraic equations and all the techniques behind the hood. And so if you're curious about how all this stuff works, we're happy to share this with people because we're also looking to find more people, both for MIT and Julia Hub, who want to work on symbolic numeric methods. So yeah, that's also throwing in there the pitch that it's also a really, really, really cool subject to do symbolics of differential algebraic equations. So if you're curious, you can dive into how the simulators are different. But yeah.
You mentioned really briefly sort of the size of the network in your modeling case, quite small, and it seems like maybe that's like a motivating aspect of this in general. Are you or people who work on this interested in that as like it allows you to apply more complex optimization procedures, like new methods being more for these problems?
Yeah, I mean, we do end up using a lot of Newton methods or truss region Newton and things like that. Just because naturally getting second derivatives and higher is much easier if you have smaller, less numbers of parameters. I mean, I don't think that we necessarily do it because we want to do these other optimization techniques. It's more of an aspect of it's more of an aspect of we kind of have this hypothesis internally that's like if you can't do this with a small neural network, then you maybe might be doing something wrong, right? If you stick to that idea, right, then generally if you make your neural network be large enough, there's a lot of theorems that show your neural network is large enough, your loss function, every local minimum becomes a global optima, and so everything works out, right? So we already know that that's going to be the case, and there's a lot of people that work on this, extremely large neural network limit. So we've instead kind of working on this type of other side where you just say, okay, if we let the neural networks be small, there will be convexity issues, there will be all these other issues, but you'll end up with something that is definitely faster because everything's going to be simpler, less parameters. What is required to be true for this to work? And a lot of the actual papers that go into the details of the methods have been mostly focused on what is required to make small networks numerically stable, and it basically gives you a nicer foundation to build off. Because I mean, to get the larger networks, you just pump the numbers up, but you still get all the stability improvements and such. So it kind of has given us this sometimes if you put training wheels on, it forces you to just make sure that you build things better, right? I think that's a decent part of it. And so some of the work that's coming out soon will be new loss functions that are more data efficient and such. And it really comes from this idea of, we work in this constrained environment. And also a lot of the folks that we work with, especially in industry conditions, they only have small amounts of data anyways. So they'll be like, okay, we built up a lab to be able to get data from this new refrigerant, like R32 refrigerants. And so, it costs us $10 million a day per data point, right? We've got 21 data points, we're like, oh, can we get 3,000? No, that's never going to happen, right? So when we work in these kind of scenarios, it just naturally forced us towards a different form of machine learning that just kind of understood there's cost issues with getting more data. And so big neural networks are just way, way, way overfitting in a way that's not helpful. Maybe we can slim this down a little bit, but still get the properties that we want in machine learning, some universality. And so that's how we kind of ended up in this interesting part of SciMo, I would say.
I think we're starting to get kicked out of there. So let's go ahead and thank Chris one more time. We can sell out this. And thank you for everyone joining both from Chris and Zoom. We'll have another one of these next Thursday, but it'll be for the people look for that.